about. And to answer the obvious question, yes, there will be a block diagram. And it will be a challenging block diagram. So that please, now would be a good time, it would be wise to start studying in anticipation of that particular exam. Yeah.
Are we going to be calculators, or are they going to be these kind of problems?
They will be these kind of problems. I will provide calculators. They'll be fairly simplistic, and I always appreciate approximation because, you know, keep in mind I'm old enough to have gone through university without calculators. Those didn't exist, and so we just approximated, or we used the slide rule. Electricity had been invented, but just a few people had electricity. Now, a couple of things. If you are in linear algebra or are taking linear algebra, I don't know what textbook they use, but this book by Gilbert Strang is the best one I have ever found. This one is intelligible. And Strang has online, if you go to the MIT website, his lectures are online as a companion to this book, and he gives the best explanation I've ever heard. You can walk away from one of his lectures and actually understand it. Now, given my age, that understanding lasts about 30 seconds. But since you're young, you'll carry that understanding much, much further. But this is an extraordinary book that has fantastic information about linear algebra and applications. Strang is probably the world's strongest applied mathematician. And so he approaches these things from a very, very simple, applied viewpoint. Now, we're going to start with Mohr circle today. We're going to fast forward a little bit. We're going to skip some of depending on your point of view, some of the more horrific mathematics or some of the more interesting mathematics, depending on how you feel about linear systems, and go into application of how do we solve problems utilizing the concept of Mohr circle for stress, and what is its physical significance. And so we'll fast forward a little bit. There is a program that I encourage you to download. It was written by Richard Allmendinger. It is available on his website, and it is simply called Mohr circle. It is out of this book. It's detailed in this particular book, Structural Geology, Algorithms, Vectors, and Tensors, which is a very, very nice overview, again, of vector and tensor calculus, and a series of algorithms that he has derived and makes available for, again, my favorite word, free. When you get to be my age, you have favorite words like free, senior discount, those sorts of things.
Oh, you can use that thing?
No, I can't do that anymore. So this is a very good book, and I would encourage you to download the program, or it's actually an app for a Macintosh, is really well constructed and allows you lots of flexibility. I have not yet played with the Windows version of it. What I find in Allmendinger's scripts is that the Windows version is a little bit more difficult to use typically than the Macintosh version, but it is as effective. So very, very good programs. And then the last thing is really, no one has asked me yet the most critical question: why should we be even bothering to investigate stress? What's the deal? Why should we even bother? Does anybody have an explanation other than tradition, or that I had a bad childhood, so I want to make you suffer, Why should we study stress?
The topography of,
Yeah,
like our surface of the earth.
it's exactly that. The concept of stress underlies everything we do in structural geology. Every single structure that we find is an expression, a representation of strain. Something had to have caused that strain, and that is stress. Right now, one of the more critical things that we have going on in structural geology, within the structural community, is the incredible increase in earthquake activity in the state of Oklahoma. What has happened really over just the past year, we have gone from understanding that in the subsurface, the state had, on the order of 100 to 150 faults, all of them inactive, none of them stressed. That was our understanding, and that was the state of science just a little over a year ago. To where now today we have a minimum, and this is really a significant underestimate, a minimum of 5,800 faults in the state of Oklahoma in the subsurface that touch basement or communicate or are in basement. So we've gone from about 100 to 5,800. We now know, we now understand, or at least we're beginning to understand, that all of those faults are critically stressed. That means they're very near or at the yield point. So there's great concern about what does the future hold in terms of the earthquake swarm that we are currently under, in terms of some of the critical areas. For example, there's a region, there's a type of fault that is kind of interesting, that is still as of yet undocumented, but it is seismogenic, and we've identified it seismically using the earthquakes that have occurred, that I will say is at a Coulomb angle relative to the overall Rosetta trend that cuts through Cushing, that 2 weekends ago produced a 4.5 magnitude earthquake. And there was a very important paper that has come out recently suggesting that it is possible that particular fault may produce an earthquake in the order of 6 near Cushing. Now, your original thought would be, okay, big deal. Cushing's a small town, magnitude 6, all right, so a few houses get damaged. Well, Cushing's the largest oil containment system in the United States. More oil is stored or pumped through that region in pipelines. It's the pipeline central for east-west pipelines and north-south pipelines. So more oil is stored in that area than anywhere else in the United States. And so if there were a 6, it would be catastrophic. So there, after the swarm that occurred a few weekends ago, the Corporation Commission has given an order for all injectors in the area within a certain distance. They've ordered them to shut in. If you are within an expanding distance, you're either ordered to reduce by half, or to reduce by a quarter, or to be prepared for action. And there are multiple injectors within that area, because the Cushing Field is a prime area for what we call the Mississippi play, which is the dewatering play. So there are large injectors. There's a group of us that are suggesting that the commission may want to be more proactive and may want to have anyone within 10 miles of that particular fault zone to immediately shut in cease and desist injection in the system because of the risk of that magnitude 6. The understanding of that stems from simply an understanding of stress what the stress might be in that region and what the stress might be on that critically stressed fault. And so we need to go from our understanding of Cauchy stress into the ability to determine what might stress be on a plane. Can we use this to try to determine what stress might be acting on a specific plane if we have some general knowledge about the far field system? And a lot of the concepts of stress within the crust in this region come from work that was put into this book. If you're going to go into a career in the petroleum industry, either in the extraction industry, exploration, into production, into petroleum engineering, you need to understand this book. And so I encourage you to get a copy of it. Mark Zoback is the world's leading authority on reservoir geomechanics, and he's also probably now considered to be the world leading authority on induced seismicity. He is the main scientist that the state is working with to try to help us get a handle on all of the earthquakes and on the fault systems in this particular case. He offers this course online, Reservoir Geomechanics, again, for my favorite word, free. As a student, you can sign up, you can take his course, Reservoir Geomechanics, online. And if you're going into the industry, I really encourage you to do that. It's, I think, a 12-week class. Mathematically, knowing Mark, it gets intense, but it's an exquisite course. And so I encourage you to get a copy of this book and or to take that particular course. So that's why we want to understand stress. We need to understand the state of stress within the crust. We need to understand how stress relates to the strains that we see in these various structural systems. We need to understand what is the state of stress on faults within basement, especially intraplate faults, because those can surprisingly result in large earthquakes. We're accustomed to earthquakes occurring at plate margins, and we're okay with that because that's elsewhere. But now it is in Oklahoma. We're seeing same things happening in Texas. We're seeing the same things happening in Kansas because we have critically stressed faults that we did not understand. And so, this will sound very strange, but my generation has failed to understand the importance of stress and has failed to understand the importance of these faults up until about a year ago. And so that's kind of embarrassing for people my age because we goofed up. We didn't understand it, so we have to move forward. Tim?
So have these faults always been critically stressed within the recent past?
Apparently they have been critically stressed for a very, very long time. They are below the Byerly yield limit for the most part, and what we're coming to understand, and I'll give you the 25-second tour, is if we draw the state, we have the central Oklahoma fault zone here. We have the Ouachita fold and thrust belt here. This is the Arcoma. This will be the Cherokee platform. This is Ozark Dome. This is the Wichita uplift here, Arbuckle uplift there, Anadarko Basin here. This would be the Anadarko Shelf, and then this is the Cimarron. Apparently, what has happened is that what we're coming to understand, and a former student that did her master's here with me is now finishing up her doctorate, Molly. Molly's done an incredible job. She's really, I think she's going to blow people out of the water. She gave a presentation to AAPG that was just stunning. What apparently has happened is that the Wichita block, Tim, has displaced from a region in here. And so we have this much thrusting and strike slip that has reactivated this in a little bit of right lateral. We have a rigid system here in the Ozark Dome. And so the faults are actually curving around, and there's a fault just to our north that just scares me to death because it is long enough, and if it has enough strain on it, it could produce a very sizable earthquake. We have out of this system, we have the Seminole Arch, this is the Wilzetta, that's the Keokuk, and the Cushing, the Mika Prague was at a Coulomb angle to this. The structure coming through Cushing is the same Coulomb angle to that. And so the magnitude of earthquakes that can occur on these systems is a function of what's the remaining strain energy density across the fault. What's the total displacement possible? If it releases, what's the area of the fault? What's the length of the fault and the area that will slip in a system? This is of a large enough fault size that it could be upward of 6 magnitude. This fault up here, I dashed it as incomplete, but it's long. May be higher, may be greater risk. We don't know yet in that system. So this displacement here is what caused most of the faulting in the basement that Mariah's been working on, most of what's going on in the Cherokee platform. There's a very interesting flexural relationship up here. Last summer, Mariah did a really neat project showing where the forebulge would be. Remember, we talked about the flexural forebulge, and the earthquakes go normal, not strike slip here, which is very cool. That has Secretary Teague very interested, by the way. So we have an intriguingly complex system, but over 5,800 fault segments in this particular system. And the Wichita uplift, the Wichita block appears to be the cause. It appears to be the bad boy on the block causing all the problems here, okay? So you've got something displacing apparently tens of kilometers, resulting in this faulting, and this is our rigid beam that everything is trying to flow around. And so we have an intriguing stress field. It's emerging, and as the researchers work on this, Austin Holland just put out a fascinating paper, fascinating analysis of the critically stressed faults. And I think right now today we have to assume that all of the faults in basement, in the mid-continent region are critically stressed, which is a huge change for us and a huge change in mindset. And so that's why understanding stress is critical for us, because it may impact our future, it may impact our quality of life, and it may actually result in damage. Because if this thing rips, and there was a paper that came out 2 days ago in the Seismological Journal of America that I got a copy of, that sort of sets off some pretty intriguing alarm bells in that particular system. So this is why we're studying stress. This is why we want to try to understand stress. And so I will get off my soapbox here. And we want to get to the point that we can begin making some simple computations, because we are up to the point that we can now write this and have a pretty good understanding of what this is. This is using Einstein's notation or indicial notation for a 3x3 matrix. If we treat this as an XY coordinates, do you want XY or 1, 2, 3? Which would you prefer? XY?
Let's do that.
So that if we look at this, this is sigma XX, sigma XY, sigma XZ. So we keep I constant, then vary through 1, 2, 3. Then we change this 1, 2, 3, change this 1, 2, 3. Where did it go? There it is. So then we have sigma XY, YY, sigma YZ, sigma XZ, sigma YZ, sigma ZZ. Okay? This describes a tensor. This is a second order tensor in this particular system. But to us, it is functionally useless because we can't measure. I have no way of going into a system, having my little probe, preferably hooked up to my iPhone, and can come up here and say, oh gosh, look at the stress. I can't walk around. It is so nice to have a tricorder. Since we're coming up with more Star Wars things in the recent Star Trek movies, it would be so cool to have a tricorder that you could walk around and go, holy moly, look at that. The stress on this particular fault is at the critical point. Anything that happens is going to trigger an earthquake. And yikes, that earthquake's going to be a magnitude 4.6. We can't. We cannot do that. What we have to try to do is, first off, we have to find a way to solve this stupid thing. If I look at this as a linear set of equations, I've got 6 unknowns, 3 equations. So, can I solve it? No. I can fake it. You know, I can go in and say, all right, 6. Done. But that would be a meaningless type of solution. So we have to find a way to reduce the number of variables. And the easiest way to explain it is in terms of linear algebra. How many of you have had linear algebra? Okay, if you've had linear algebra, we're going to use some big words. We're going to come in here, and what we will do is we are going to fully diagonalize this matrix. We are going to determine the eigenvalues and eigenvectors. Poof, we're done. And we've resolved the issue. If you've not had linear algebra, that was as if you were talking to a Martian. Has no meaning whatsoever. But the idea comes back to, if I have a system, I know that some of these are normal stresses, some of these are shear stresses. These along the diagonal are normal stresses. These are shear stresses. So, if we have a plane, and I'm going to make it a finite plane just to make life easy, or I'm going to get a really big magnifying glass and enlarge an infinitesimal plane. If I have a system where there is my stress, I can talk about a normal component and a shearing component there, based on some coordinate system. Are we good so far? What I can do is I can rotate my coordinate system. Remember, coordinate systems are fluid. I know that the physicist, this drives the physicists crazy, this probably drives the engineers crazy, and I know it drives the mathematicians crazy, but we can move that coordinate system, we can transform that coordinate system any way we wish. And so we can rotate that coordinate system to the point that the only thing we see is normal stress. So what I'm going to do is propose is rotate to a coordinate system where shear stress uniquely goes to 0. Okay? So, if you are a linear algebraist, we can do that. Strang has a beautiful chapter on that. The book by Fletcher and Pollard has a beautiful chapter on that. But we're going to choose a coordinate system.
Are we rotating the matrix then?
We're going to be changing the individual values of this so that these are going to go to 0 in the limit.
So this is invariant?
Yes. So what we're going to do is we're going to find what those invariants are. Okay? We're going to find the invariants of the first order. There's going to be invariants of really 3 different orders in this particular system. But Tim, we're going to find what those first order invariants are. If we can do that, what we are left with now is a matrix where we have sigma 1, 0, 0, sigma 2, oops, I went the wrong way, and sigma 3. Now, the really strange thing, the really odd part of this is that this and that tell us the same thing. These two are equivalent. What we've done is we have transformed our coordinate system, where we're looking here at what I'm going to call principal stress space and real stress space. And we just need to find out what this monster looks like. What does this, now that's not a transpose. If you're in linear algebra, I did not just transpose. That is a transformation. If you would prefer, I can give it an M for map. We have just changed our coordinate system. That's the beauty of basically the interactive capacities of coordinate systems. If you don't like that one, okay, fine, we're going to do this one. Or we're going to make it polar, we're going to make it elliptical, we're going to make it this weird, irregular coordinate system. And we can just map back and forth depending on what we want to see. So, these two, can you accept that if we rotate to a coordinate system where our shears go to 0, then we have a perfectly diagonalized system. These are what we call our principal stresses in that system. And now we have, 3 equations, 3 unknowns. Life's easy. Yeah.
What were you calling the principal stresses?
These, right here.
Okay.
Those are the principal stresses for a particular system. Now, there's got to be a way of showing how do we get back and forth. Because if we transform, if we map from one coordinate system to the other, we have to be able to map back. if you've had differential equations, ordinary, you may have done, maybe they might even do it Calc 3 now, Laplace transforms.
Yes.
Well, it's real easy to do the Laplace transform one way. Finding the way to get back can sometimes be horrendous, to find how to get back into your system. We want this to be a nice, easy way of transforming. So what we have is this tool becomes a very interesting structure for us that we're going to call Mohr circle for stress. And by the way, we just blew through about 10 pages on the course notes. So we fast forwarded through some of the juicy parts. The Mohr circle for stress is kind of an intriguing construct. We're going to think for now in a two-dimensional case. We're going to do Mohr circle for 2 dimensions. If you want to play with 3-dimensional Mohr circle, it's actually quite a lot of fun. You can grab the application, the app from Rich Almendinger, and he has it set up by default to be a 3D set. And then you can play. It actually has some really cool things. It was fun playing. It's a lot of fun to play with. But what Mohr circle for stress does is it puts us into a very, very simple graphical form where we have shear stress here, which I'm going to call it tau. This is shear stress. This is normal stress. The sign conventions that we are going to use, if you look at the handout, and I bring a copy from, maybe I didn't. I guess I left it on my desk. From last time, it lists the sign conventions that we're going to use. The basic sign conventions that we are going to use is that compression, oh, thank you. Sure. It's this one here. 2 sides. The sign conventions, thank you. I just wanted to
Okay.
point it out. The sign conventions that we're going to use here is that this is going to be compression, and we're going to view compression as being positive. This is going to be tension, tensile, and tension is negative. This is going to be a positive shear. This is going to be a negative shear in that particular system. Okay? So that when we look at trying to resolve some of these systems, this is going to be the map that we use. Now, the things that we need to know about Mohr circle. Can I, well, I hate killing those two. Let's do this. Well, we're going to look at here. Let's say that we have known values or can approximate sigma 1, sigma 2. We then have a circle here that fully describes in 2 dimensions all of the normal and shear components that can exist on a plane. Okay? This is a circle, this will sound strange, in degrees to theta. Yeah.
I just want to confirm, will all the principal stresses then have to be plotted on the axes?
Yes.
Okay.
Since we're here along the diagonal, those can only occur along this axis. They cannot occur off axis in that system. This is a circle in degrees to theta, whereas in the real world, we think in terms of circles that are at degrees theta. And so we need to figure out what's theta in that particular system. And so if we give an example, let's say that we have the following. Here is a cross-section. Let's say that's east, this is west. Here is a fault plane. And let's say on this particular fault plane, we can approximate. So we're going to refer back to Zoback. And Zoback's going to say, oh, well, your sigma 1 value for this region is, let's say we have a sigma 1 value here, and we're going to make that 7 gigapascals. We're going to have a sigma 2 value here, and that's going to be 1 gigapascal. The question that we have here is, what's the normal and shear component on that fault or on that fracture? So our question is, what is the normal and shear components on this plane? Well, sigma normal and sigma s relative to the plane itself. So we're going to transform back and forth from real world to our principal stress world in the same basic diagram. Okay? So we need to know a little bit about this. We need to know the dip angle. What's the dip angle of the fault? What is the plane normal? What is the angle from sigma 1 to the plane normal? So theta is the angle from sigma 1 to the plane normal. If sigma 1 is anticlockwise, or if theta, is anticlockwise, it's positive. If it were clockwise, it would be negative. That's one of our sign conventions for Moore's circle. So, how do we solve the problem? Well, if this is, let's say this is 70 degrees, that means this has to be 20 degrees, right? Okay, so now we're going to do our plot. We're going to carefully, this is sigma 2. This is sigma 1. We're going to plot our circle. We're going to find the centroid here. And we're going to go degrees to theta, or 40 degrees. I went too steep. Up. This is theta, it's 20 degrees. This is a circle in degrees to theta, so with 2 theta here would be 40 degrees, and it's positive. So this point right there, that is going to be sigma in sigma s. There's our shear stress value. There's our normal stress value on this plane. Yeah.
Okay, you mentioned something about clockwise being negative.
Yes. If theta were down clockwise, then it would be negative. And the simple example, Steve, would be if we had our plane, let's say that our plane was dipping this way. Again, sigma 1, sigma 2. Now my plane normal is out here. Theta is clockwise, so that would be negative. And I would then come over here and plot down here in the negative zone. Okay? So, if we can approximate through techniques used by Zoback or introduced by Zoback, or the way we're going to do it, just assume some values for our principal stresses. And if we know the orientation of a fault, of a fracture, we can then predict the normal and shear stress across that. And what is happening, Dr. Holland, Austin Holland, he used to be the state geophysicist. He is now out at Albuquerque at the National Earthquake Information Center. But what Dr. Holland is doing is he is resolving this out using Moore's circle, using earthquake focal plane solution mechanisms to generate a proxy for stress, to then determine which faults in the state are critically stressed. And he's doing it by proxy through a rather intriguing set of computer programs in that system. So, this is a pragmatic, easy method as long as we are careful. We want to be extremely careful about the way we structure these. We want to make sure we get our angles correct. We want to make sure we get our values plotted correctly. And then that tells us that will feed back. And if I use my scale here, that looks like about 2.7 positive shear. And that looks like about 6.1 normal stress on this. So if we know what that stress value is, we can predict potential for failure on a system. Now, we have, unfortunately, no time. I have a challenge for you. How would you like to do this? Since it's homecoming, do you want me to be really nice and not hand this out? Or would you rather suffer this weekend.
Could we do it next week?
I can hand it out and then we can do it on Monday in class. How about that? So you can have a lovely weekend, you can go to Oktoberfest, you can have a good time, you can go to homecoming, you can have a good time, realizing that on Monday, isn't that right on? Now, the cards that you have, you'll notice that the cards that you have for today have a number on it. That is your group for Monday. Rarely happens. So enjoy.
باخذه في اسمه باخذه السيدي انا